just the fact of having a cold. Good evening, ladies and gentlemen, and welcome tonight to our Griffith Impact Lecture. I'm Robert Sang. I'm the Dean Learning and Teaching in the Griffith Sciences Group. I'm proudly also a physicist, as I mentioned earlier, a quantum physicist, and a member of the Centre for Quantum Dynamics, where our two speakers tonight are also members of that centre. In fact, Howard is actually the director of the Centre for Quantum Dynamics. Let me first begin by acknowledging the traditional custodians on the land upon we meet today, pay our respects to our elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islanders. I'd also like to acknowledge our deans in the Griffith Sciences Group here tonight, so Professor Cecilia Chang, Professor Hamish McCallum, and Professor Fran Sheldon. So, Fran, thanks very much for coming along tonight. I'd also like to acknowledge our academic colleagues from other universities and research organisations. So we have people from Central Queensland University, QUT, RMIT, University of Queensland, CSIRO, and the Queensland Museum. And we also have a range of teachers and heads of science departments from of our local schools, from Fairholme College, Glenalla State High School, Keebra Park State High School, and Education Queensland. And I know this is a really busy time of the year for teachers and at schools, so I thank you very much for coming along tonight. So, welcome to our last Griffith Sciences Impact Lecture tonight, and that's on the Big Bell Test, D-Day for Quantum Physics. So tonight's event is unique in that as we're working in tandem with over 30 universities and research organisations from across the globe to take part in a very large public science experiment called the Big Bell Test. Our speakers tonight will actually discuss the intricacies of the physics around this, but the test is really interesting in the sense that it's actually using participants from all around the world that are non-physicists to use their input actually to drive these experiments, in particular to get randomness, which they really need in these experiments. And Geoff and Howard will talk a little bit later as to why this is really important. Actually, it's really very interesting for timing for this experiment, because one of the definitive experiments which had been mentioned in the flyer was done by a guy called Alain Aspère from France. And next week we have one of the largest physics conferences that we've held in Australia, actually happening at the Convention Centre. In fact, we have last year's Nobel Prize winner in physics, Kajita, coming along. But also one of our plenary speakers is Alain Aspère, who actually performed that test. So it's actually good timing, and if you sneak in, I'm sure we'd turn a blind eye if you wanted to look at that talk. But equally, there is a public lecture on Monday night from Kajita talking about neutrinos and how they were detected and why he actually won his Nobel Prize around that. The idea of actually bringing science out to the public is very important, and we recognise that obviously in Griffith Sciences, and I think the influence that we're having in science, engineering and IT with our communities is one of the great driving forces behind holding events like this, so we can actually publicise that. We started our impact events almost 3 years ago with the goal of engaging the public with the diversity of science, engineering and technology endeavours that we undertake in our university. This year, the discussions and presentations have been wide-ranging. Last month, we had a presentation on the groundbreaking research on the first genomic study of Indigenous Australians through, and I'll talk about some other topics that we've also discussed, but I want to bring up that particular study because it was published in Nature. It hit the front page of the New York Times, and obviously it was a great scientific impact in terms of actually demonstrating that Australian Aboriginals were the first Indigenous Australians. But the other component was the social impact. In that publication, and it's quite unusual, there were 7, I think, Indigenous elders who were co-authors on this paper. So they were actually not just studies or used for studies, they were actually participants and partners in the research. And the other component that was really important about that was the influence it has on society. You know, that we've had a Senate at the moment that are debating whether or not to include Aboriginals, Indigenous Australians in the Constitution and recognising them as First Peoples. And there are senators, you know, on the record of saying, well, how do you know that they're First Peoples? Well, now we have the scientific evidence to back that up. And it's interesting to talk to Indigenous Australians and to see their reactions to that, to say something that, well, we knew about that already, but it's nice to have the scientific evidence behind that. Okay, so just some of the other topics that we've actually talked about in recent times is securing Australia's food and water systems, meeting the challenges of climate change, and sports engineering with our industrial partner JBED Technology. So although this is the last Impact of the year, and I'm sorry about for the advertising, please subscribe to Impact and be the first to receive our invitations to come to our events, which are held every 2 months in Brisbane. And join us in some of the discussions around the challenges, but also the fantastic science, in fact, that we do at Griffith, but that has this great, as the name of the lectures suggests, great impact. So the format of tonight's evening is actually going to be quite simple. We're going to hear from our two speakers, and then we'll actually open the floor up for a bit of a panel discussion, so for people to have the opportunity to ask Howard and Geoff questions about the talks tonight. And then afterwards, we've got some goodies, so if you want to stay and have some drinks and some nibblies, we'll have some of those afterwards. If you are on Twitter, please follow us at Griffith Sciences. Use the hashtag GUI Impact. And if you've got any questions or comments about this evening, you can actually pop that in there. And we're also live streaming tonight on YouTube. Is that right, David? So be on your best behaviour. And that'll be available on our Impact website following the event. So let me introduce you first of all to our first speaker for this evening, Professor Howard Wiseman, a colleague, very good friend of mine, and I gave him a long service medal yesterday for 17 years. Congratulations, Howard. Really interesting discussion because Howard and I were young scientists 17 years ago when Howard was interviewed, and I was asked to take Howard out for lunch. So it sort of feels a bit weird, giving Howard then a long service medal 17 years later. But congratulations for that, Howard, and you've been a great academic within a great scholar within Griffith University, and of course the broader international community. So let me tell you a bit about Howard. So Professor Howard Wiseman is an Australian theoretical physicist. He completed his PhD on quantum measurement and feedback theory at the University of Queensland in 1994. After a postdoc in Auckland, he returned to Queensland in 1996, and if I remember, that was as an Australian Research Council postdoctoral fellow. He's been at Griffith University since 1999. He's actually been a Federation Fellow since then as well. Very few people actually receive those fellowships. And he's also been integral as the director of the Centre for Quantum Dynamics since 2007. And when that centre was formed, what year was that formed? 2003. There were 4 members, so 50% of them are here tonight. So Howard's best known for his work in quantum information, quantum foundations, and quantum measurement and control. He's also known for his work in Arthurian history and literature. And Howard's one of the few people that I know that's contributed, at least in our university, in an area of quantum physics, theoretical quantum physics, but also in history. And I think you actually contributed to the era coding, the way that we actually rank so across in history as well as in physics. So Howard, it's a pretty diverse interest that you really have. And just to let you know, he's written a book, and I'm sure you'll tell people about that tonight so we can sell lots of copies again, Howard, about this. But he actually took long service leave in order to write his book on this. So the other thing that Howard's done professionally within physics, he's written 2 books and over 200 refereed journals. He's won a number of national prizes, including the 1994 Bragg Medal for his PhD thesis, the 2003 Pawsey Medal, the 2003 Malcolm McIntosh Medal. He's been elected as a Fellow of the Australian Academy of Science, a Fellow of the American Physical Society, and just recently he's been awarded as a Fellow of the Optical Society of America. So without further ado, Howard, I'll ask you to come and give your presentation.
Thank you, Robert, for the very kind introduction. I just need to switch to the talk. All right. Is that the one? Okay, thank you. Thanks again, Robert. Yeah, so it's great to be here. Great to see people turning up. So I'm going to be speaking for roughly the first half of the evening, and then Geoff Pryde, who's the Deputy Director of our Centre for Quantum Dynamics, will be taking over. Yeah, and I'll explain why. So I want to talk to you about the Big Bell test, the theme for this evening, harnessing your free will to reveal the nature of the universe. Okay, so as probably most of you know, this fits in the context of the weird and wonderful quantum world. So why do I call it weird and wonderful? Well, I'll be talking a lot about the weird stuff, but just as an example, so this is Richard Feynman. Many of you would have heard of him. He's probably regarded as one of the great geniuses of the 20th century, who won a Nobel Prize for his work in quantum physics, and yet he said this: I think I can safely say that nobody understands quantum mechanics. Okay? So I think it's fairly rare to have somebody who's got a Nobel Prize in an area to say that nobody understands that area. But that gives you some idea about how weird quantum mechanics really is. But then it's also wonderful because even though we don't really understand it, we can still use it to do all sorts of wonderful things in technology. So in particular, both Geoff and I are in an Australian Research Council Centre of Excellence, which includes a number of other Australian universities, are called the Centre for Quantum Computation and Communication Technology. So these are just two examples of the things that can be done using quantum weirdness that I'll talk briefly about, and Geoff will talk briefly about in his talk. Okay, so that's the context. What's the Big Bell test? Well, as Robert said, it's an international project which is happening, like the D-Day, the day that everything is happening, is right now. But it's not too late for you to be involved. So if you go to their webpage, which is thebigbelltest.org, and so this is a summary of what it's about. The Big Bell test is a worldwide project to bring human unpredictability or randomness to cutting-edge physics experiments. It may be surprising, but there are aspects of physical reality that can only be understood by asking unpredictable questions of nature. The most famous experiment of this kind is the Bell test. So that's why it's called the Big Bell test. And so in the remainder of my talk, I really want to explain to you what a Bell test is and exactly what human unpredictability or randomness can do in the service of a Bell test. Okay. So this is an outline for the rest of my talk. So to begin with, I want to go back to sort of the birth of quantum mechanics in this decade of 1925 to 1935, because that really sets the scene of what happened. And what happened, the big year was 1964 when Bell published his theoretical paper, and then that gave rise to 50 years of experiments in this area, culminating in experiments just last year, which I'll talk about and which Robert mentioned. Okay, so then after I've explained then what Bell's theorem is, I want to talk briefly about, as I've said before, what it's good for, and then concentrate more about what it actually means, because I think this is important to understand how human unpredictability can actually play a role in doing a Bell test. And then I'll finally get back to exactly what the Big Bell test is, and then hand over to Geoff. Okay, so 1925 was the year that, by some ways of looking at it, that quantum mechanics was invented. So this was the year that this very young physicist, Werner Heisenberg, so he was less than 25 years old himself at the time, and came up with this theory. So there was some quantum theory which already existed. Some of you might remember the idea of electrons going around certain orbitals in atoms. This idea existed already, but nobody really could explain why things were like the way they were. So what Heisenberg did, said, okay, so I'll let him. Okay, so when I have things in this font, this is not really what Heisenberg wrote, okay, or said, but this is a paraphrasing, perhaps, of what he said. Anyway, so here's Heisenberg saying, would you believe that by thinking about the emission of light from atoms, so here's a photon coming out of an atom here, I came up with the idea that a physical quantity, like position or velocity, should not be represented by a number, but by a matrix of numbers which could be infinitely large. Okay? So a matrix of numbers is just an array, a square array of numbers like this. And Heisenberg had this radical idea, why don't I say that instead of the position of the electron is some number, that it's this infinitely large array of numbers. Like, well, what the hell does that even mean? But who knows? But in any case, using this idea, it was possible to derive these properties of atoms, like the fact that they had quantized energy levels. So these energy levels, which previously had just been postulated, now it was possible for Heisenberg and his colleagues to actually derive those. Okay? And it's because that he gave rise to quantized energy levels that the theory he came up with is called quantum mechanics. And that was really where it started. Okay, so as I said, this is just a crazy idea. What does it actually mean? Well, it took a couple of years for people to get their heads around and then try to think what it actually meant. But in 1927, Heisenberg and his older colleague, Niels Bohr, in Copenhagen, came up with their interpretation, which was then named after the city where Bohr had his institute. And so this is the rough explanation. So again, Heisenberg's talking here. The matrix representing, for example, the spin of an electron does not tell us its value. It tells us only the possible values we may find if we measure it. Okay? So here it turns out that the matrix for the spin of an electron is quite a simple little matrix here. And what that tells us, there's a way of analyzing this matrix to tell us that the possible values that the spin could have if you measure it are, in this case, plus a half or minus a half. Okay. So the conclusion, though, that Heisenberg drew is that before the measurement, the spin has no value. It is the act of measurement itself which creates the measured value, plus a half or minus a half. And Bohr went on, in other words, our understanding of reality in the normal, or the more technical words we physicists use, macroscopic or classical world, does not apply to the microscopic or quantum world. Okay? The idea that variables or physical properties have values just doesn't apply in the quantum world. And Bohr thought the nature of the quantum world is and will forever be unknowable. Okay, so this was a pretty huge philosophical conclusion to come to on the basis of some mathematics. And not surprisingly, not everybody was happy with this conclusion. In particular, there are some fairly famous people who are not happy with this conclusion, including Albert Einstein and Erwin Schrödinger, the Austrian physicist. So both of them actually published Dissenting Opinions in 1935. Things sort of came to a head there. And so here's Einstein saying to Bohr, because he really wrote a paper directly addressing the Copenhagen Interpretation and criticizing it. So here he's saying, I can't accept the way measurements create reality in your interpretation, Bohr. The whole idea of measurement is vague. Will a sidelong glance by a mouse suffice to be a measurement? And so that's an actual Einstein quote, okay? You can tell by the different font. So he really didn't like this idea that the theory used the concept of measurement and said that when you make a measurement, things become real. What's a measurement? Like, we don't have any physical principle that says that something is a measurement and something else isn't. Can a mouse make a measurement? All of this was vague in Bohr's theory. So Einstein really didn't like this vagueness. He thought that everything should be precise, that physical quantities must have values prior to measurement. Okay? This measurement stuff is nonsense. The values must always be there. A proper interpretation of quantum physics, he thought, with hidden variables, okay, giving the precise values, will ensure this and will also remove action at a distance. Okay, what's he talking about, action at a distance? Well, so this was something that Einstein brought up in 1935 and that Schrödinger also wrote about in 1935. Okay? So he's saying the action at the distance, which Einstein rightly worries about, comes about when two particles have interacted and therefore become entangled. Okay, so this was a word that Schrödinger introduced and is really a thing that doesn't exist in classical or macroscopic physics, but does exist in quantum physics, that when two particles have interacted, somehow they stay connected. Okay, and a consequence of this, as Schrödinger pointed out, following what Einstein had written, is that what happens is that when one particle is measured, the result, when you have an entangled pair of particles, causes an instantaneous change in the state of the other particle, no matter how far away it is. Okay, so that's the action at distance that Einstein didn't like and which Schrödinger also didn't like. The fact that you have this weird effect, not only does measurements on a particle create the value, when you have entangled particles, a measurement on this particle can create something on the other particle instantaneously no matter how far away it is. Okay, and for Einstein and Schrödinger this was just unacceptable. Okay, this idea, and they really thought that well, Einstein in particular thought that if we had a better theory which had hidden variables, which had extra variables which we can't directly see, that would solve this problem of action at the distance. Okay, so you might think that there's this huge debate going on in 1935 that physicists would have kept working on this and worked it out, but actually that's not really what happened, and I suppose it's because the war intervened and then there were just a lot of other exciting other things to work on, and so really not very much happened in this whole field until 30 years later in 1964. And that's when the physicist from Northern Ireland, John Bell, came up with his famous theorem. Okay, and I'll let him explain. So Bell is saying, I have proven a theorem. Okay, so a theorem is something where you start from assumptions and just work it through logically and come to a conclusion. So it's just basically if you agree that it's logical, then you have to agree that it's true. So a theorem showing that Einstein was wrong. His idea of hidden variables cannot remove the action at a distance in quantum mechanics. Okay, it doesn't solve the problem. When you have quantum entanglement, the theory predicts correlations between distant measurement results that cannot be explained without non-locality, okay? Without this instantaneous transfer of information across a distance, which Schrödinger and Einstein didn't like. Bell showed that that was necessary if you actually wanted to explain the correlations, the way that a measurement result here and a measurement result here could be related. You had to invoke this type of non-locality or action at a distance. But Bell, like Einstein and Schrödinger, found this very unsettling, and he really wondered, as Schrödinger had in particular, can nature really be so strange? So the point was that nobody had actually done an experiment at this point to test whether these correlations really existed. So possibly the answer was that, so Einstein was wrong to think that hidden variables could explain these correlations, but maybe the correlations just don't exist. Maybe quantum mechanics doesn't actually apply when you really stretch it to these distances with entangled particles. And so it took a few years, but gradually people started to learn about what Bell had done, and then of course they wanted to know, do these correlations really exist in experiments? So the first experiment was done in 1973, but it was pretty crude, and really it's taken all of these decades, up to last year, to gradually make improvements on these experiments until what was regarded last year as really the definitive experiment. And yeah, as Robert said, so Alain Aspect, who's going to be here next week, he was one of the key people in this development, but it was really last year that an absolutely definitive experiment was done, and in fact not one but three, okay? So many people around the world was interested in this that there was a real race on to get this, to do this first definitive Bell experiment. And so three groups all managed to do it last year. So I'm going to just put up a photo of one of these groups. This is from Vienna, so I'm choosing this one partly because I think this is just such a great photo. It really looks like a scientist working, doesn't it? So this is Marissa Justina, who was the first author on the paper from the Vienna group. Well, so I'm sure you're wondering what was the result. Okay, what was the result of this experiment? Is there really Bell non-locality, or is quantum mechanics wrong and these correlations don't exist, as Bell suspected might be the case? I'll let Marissa talk. We have created pairs of entangled photons and sent them, so photons are just particles of light, right? Sent them to two labs more than 50 meters apart. So in fact, we can see that the other lab is literally down the corridor here. Okay, so there's one lab here with this apparatus and a very similar apparatus 50 meters away down that corridor. There we performed at precisely the same time measurements of the polarization of those photons. So polarization is just one of those variables like spin, which has only two possible outcomes. So it's a nice thing in that way. The results of these measurements show the type of correlations John Bell used in his non-locality theorem are exactly as quantum mechanics predicts. Okay, so these correlations with no explanation, without action at distance, are real. Okay, they've been seen in nature. There's just no way around it. Quantum mechanics is an accurate theory, but there's just no way to explain those correlations by thinking in terms of hidden variables or any other explanation that doesn't involve faster than light action. Okay, so faster than light action, you're going to ask, oh, can we use these correlations to send signals faster than light? No. Okay, the answer is no. Unfortunately, it just doesn't work like that. So even though there seems to be something going on faster than light, we can't use this effect to signal faster than light. It just doesn't work like that. So how does it work? Okay, what are these correlations like then? Well, one of the explanations, which you'll sometimes read, is that Bell correlations are like having two dice, so one in one lab and one in another lab, and whenever you roll them, they always come up the same. So they always come up a 1 or a 5 or whatever. Okay, they come up randomly each time, but every time both of them come up the same. So that is a pretty weird pair of dice. Okay, if you had a pair of dice like that, I'm sure you could make a lot of money, but that's actually not what Bell correlations are like. Okay, because those correlations, although they're really weird, okay, they could be explained by a local mechanism. Okay, a clever enough engineer could put a little tiny motor inside each die, okay, with a clock, okay, so that when the die was rolled at a particular time, it would always come up with some particular number on the top, and the other die, being identically constructed, would do the same. Okay, it's possible to do that. And so although it sounds unlikely, there is a possible explanation for these correlations by a completely local mechanism. Right? What Bell's theorem showed is that the correlations in quantum mechanics just are not like that. Okay? So they're not just odd correlations, they're really impossible correlations unless you'd allow some signaling, or I shouldn't say signaling, some sort of action at a distance or information transfer faster than light. So this is what Einstein thought things would be like, that it'd be some complicated theory with mechanisms inside particles, and it just doesn't work like that. So it's a nice idea from Einstein, but no dice. Okay. All right, so how do we actually find these Bell correlations if they're not correlations like this? Well, unfortunately, I don't have time in this lecture to explain to you how we characterize Bell correlations. I give other talks where I do that, but what I want to just get across here is some of the key aspects to them. So first of all, we have to have two different laboratories, as we talked about, like they're separated by some large distance, and conventionally we talk about having two experimenters, Alice and Bob. Okay, they each have one of these labs, and the crucial thing is that, unlike the dice example, is that Alice has to be able to make a choice about what property she's going to measure on her particle. Okay? And she has to be able to measure for a Bell test at least two different properties of her particle and randomly choose which one she's going to do, and Bob has to be able to do exactly the same. Okay, he also has to be able to randomly choose. So this is the crucial thing about a Bell test, which is where choice and unpredictability get fed into the experiment. Okay, so I'll come back to that later. All right, so I've sort of explained what these Bell correlations are like, that they're impossible to be able to be explained by a local mechanism. But you might, so in that sense, it's sort of like, you know, a superpower in that you've got these correlations that if you had, wouldn't matter how many computers or whatever you had in those labs, you wouldn't be able to produce those correlations without these entangled quantum particles. Okay, it's just this amazing thing that you can do with quantum physics, but you can't do any other way. But you might be thinking, well, yeah, all right, but doesn't really sound like a very useful superpower. I mean, it's sort of like the superpower of being able to fly through the air, but only when you're already on a plane. Okay, so yes, this is a superpower, but what does it get you? All right. Well, it turns out that it actually does get you a whole bunch of things. So more generally, entanglement, that what you need to start with Bell tests, That's a phenomenon that lies behind lots and lots of physics. Okay, so understanding that better is crucial for all sorts of physical technology which we are creating. And in the future in particular, entanglement is going to give rise to new types of technology called quantum information technology, and this is already happening. And so in particular, so Bell-type correlations, the exact type of correlations you have in Bell tests, it's been shown that that allows absolutely secure communication between two agents, like between Alice and Bob, if they can do that. So secure in the sense that they can be sure they can exchange a message and be sure that there's no eavesdropper who can also get that message. Okay, so this is the idea of quantum communication. That's something that Bell tests allows. Entanglement more generally will allow a phenomenon of quantum teleportation, and again, unfortunately, I've not got any time to tell you more about it, but if you use quantum teleportation, you can actually scale up quantum communication to a global scale, and that's what we and many other people around the world are working on as a technology. And then finally, there's the technology of quantum computing, which uses entanglement and which can solve some problems in a finite time that on any conventional computer that didn't use quantum effects like entanglement, it would take them basically forever. Okay, so immensely powerful computers for solving certain types of problems, and again, that's something that we're working on in our center, and it's happening in many other places. Okay, all right, so finally I want to talk about what we make of this all. Okay, so getting back to the sort of the more philosophical take, Geoff will talk a bit more about the technology. Yeah, what conclusion do we draw from these Bell tests, okay, that have been done? What does it tell us about the world? Well, to answer this, we have to look a little bit more carefully at the assumptions that actually go into Bell's theorem, okay? Because Bell's theorem says that these correlations that quantum mechanics predicts can't be explained by any theory which satisfy the assumptions that he made. Okay, so we have to look at those assumptions, and some of them are going to look like so obvious. You'll say, well, why do you even have to write that down? Like, who on earth would ever, doubt that? But you'll see that things are not so simple. Okay, so the first assumption I'm going to call macro reality, short for like macroscopic, everyday reality, is the idea that just when Alice, or Bob obviously, makes a measurement, she gets a result. She gets one result and only one result. Right? And that this is something that really happens and it's not just an illusion. All right? We actually have to make this assumption, as you'll see. Okay. Second assumption, micro-reality or microscopic reality, is this idea that Einstein wanted, is that Alice's result is caused by real pre-existing properties of the system that she's measuring, and it's not just something that magically appears when this magic thing called a measurement takes place. Okay, that there's actually some physical process which turns properties into results of measurements. A third concept, which I'm going to call Einstein locality, is this idea that Alice's action cannot have an instantaneous or faster than light effect in Bob's life. Remember, these are the assumptions we're making to get Bell's theorem. Yeah, okay, I'll finish. And the final one is the assumption of free choice, which says that Alice's random choice of what to measure is independent of any pre-existing properties of systems that could influence the experimental results. In other words, that Alice really is free to choose whatever she wants to choose, and is not somehow constrained by other things that are going on. Okay, so those assumptions together is what Bell made, and they say correlations must be of this, of this form. Quantum mechanics give correlations which are not of this form. Experiment verifies quantum mechanics, right? Therefore, at least one of these assumptions must be wrong. Okay, one of these must be wrong, or at least one of these must be wrong. So which one? Which one of these assumptions do we conclude is wrong? Well, it depends who you ask. If we go back to Bohr, or the ghost of Bohr, because he's dead, I think he would say, give up micro-reality. Okay, give up this idea that the measurements are revealing pre-existing results. Bohr would say, I think, all this fuss about Bell's theorem just confirms what I said all along. There is no point trying to understand correlations between measurements on quantum systems. Okay? Measurements don't reveal pre-existing properties. The result is created by the act of measurement. Okay? We don't have to understand the quantum world to learn how to use it. We'll never understand it, and we shouldn't try. Okay, a lot of people don't like that attitude, but you know, it sort of works. One of the people who didn't like that attitude was this interesting guy, American physicist called Hugh Everett III. But he came up with a really more radical idea of giving up macro reality. So his argument went something along these lines. Bohr's philosophy ignores the very basic fact that all things, including our brains, right, your brains, everything, right, is made of quantum particles. It's made of atoms. Atoms are quantum particles. So if we say that we can never understand the quantum world, then we're just saying we can never understand anything. We're just giving up on understanding anything. And that just seems too high a price to pay. So in 1957, Hugh is saying, I propose that we should take quantum mechanics seriously as describing everything. Okay, if everything is made of atoms, then we should describe everything quantum mechanically. But the consequences of that is that because the properties of quantum particles don't have definite values, as Heisenberg showed, then nothing does. Okay? Microscopic unreality will get amplified to macroscopic unreality. So the everyday world that we seems to have definite values, that this lectern seems to be here, right? That's just an illusion. Okay? What actually happens is that every time we interact with the microscopic world, every time we make a measurement, it amplifies up the microscopic imprecision or lack of reality onto the macroscopic scale, and our reality splits. It splits into different realities, different worlds, and so this is what Hugh Everett called the many worlds interpretation. Okay, that's if you go that line. A totally different approach is one, again, from a dead physicist, David Bohm, a British physicist. So his idea would be to give up on Einstein locality. All right? And so here's his argument is this. I agree with Everett that we must try to understand the quantum world. So disagreeing with Bohr, right? But rather than concluding that the macroscopic world is an illusion, he says, I'd prefer to add something to the microscopic world to make it as real as the macroscopic world. So then everything will just be real, okay? So in 1953, in fact, before Everett even, he developed a theory that does exactly this. Okay? It gave a reality to the microscopic world by adding particles, positions to it, basically. But the price that must be paid is that we must give up Einstein locality. Okay? Because it's putting in micro-reality, we have to give up something. The thing that he chose to give up, and that has to be given up, is Einstein locality. Okay? That has to be given up, of course, because the faster-than-light effects we need to have these faster-than-light effects because it has to explain Bell-type correlations. Okay? So we have to give up something. That's the price that you pay to have microscopic reality, is to say that we really do have faster-than-light effects going on underneath things. And as he said, Bell agreed with me. So Bell actually, of the ones I've talked about, Bell was quite partial to this theory, for example. Okay, this one I was sort of encouraged to put in. This is my own crazy idea with my colleagues Michael Hall and Dirk Beckett. Yeah, it's complicated. But this is an idea that we published in 2014, which we called the many interacting worlds. So it's sort of a combination in some sense of Bohm's and Everett's ideas, in that, like in Everett's theory, there are many worlds. Okay? But unlike it, those many worlds don't appear when measurements are made or anything like that. Those worlds have always existed and always will exist, but they interact. Okay? So we are just in one world, one real world, which is real on the microscopic and the macroscopic scale. But that world has its dynamics influenced by the nearby worlds, the worlds which are very, very similar to it. And in our approach, it's exactly this interaction of our world with nearby world that gives rise to what looks like faster-than-light effects in our world. Okay? It's being mediated by the interactions in the other worlds. And again, we need something like this to explain the Bell-type correlations. Okay, as I said, I'm not I was told by Damien that I should talk about my own work, so that's my little spiel on that. Okay, but the one that I really want to get to, and because it's most relevant here, and here we have another non-dead physicist, Gerard 't Hooft, who's a Dutch physicist, and he has the radical idea of giving up the last of those four options, which is free choice. Okay, the idea that Alice and Bob are free to choose their results. So here he's saying, the random number generators used for choosing which measurements Alice and Bob perform in a Bell measurement are just physical systems. Okay? If we imagine a deterministic universe, so where everything evolves with no randomness or chance, these choices, these supposedly random choices, could have been determined at the Big Bang, the same time as the variables that end up giving the results. Okay? So if everything was determined at the Big Bang, then all the correlations that are seen in Bell experiments could all have been determined back then, 14 billion years ago, and it's all just gone forward in time, and there's no non-locality. Okay, so he's saying you can explain Bell correlations, you can explain any correlations just by recognizing that things could have all been determined long, long ago, and that's why they seem to be correlated. But, I hear you ask, he says, what if Bob uses his free will to make the choices? Surely those decisions are not predetermined. Okay, we have a feeling that I can choose to do something right now that certainly was not determined 14 billion years ago, right? I can just choose to either touch this glass or not touch this glass, right? Nothing is determined whether I'm going to do that or not. That's the feeling we have, right? What does 't Hooft say? He says, no, you have to assume that Bob has made a decision not out of free will, but by some predetermined correlation. Okay, so free will is just an illusion. That's his theory. Okay, so where does that get us? So which of these approaches should you adopt? Well, I'm not going to tell you, right? You have to make up your own mind, but what I want to talk about is this last one, a 't Hooft solution, because I think it raises a very interesting question of whether there's a difference between the random choices made by physical devices, right, physical random number generators, and the arbitrary or random choices made by human free will. I mean, I think we feel that inside us we have something which can go beyond anything that a random number generator might be able to do, but is that the case or not? So if you feel that way, okay, that human free will could really be something special, then I think you have to ask another question. Well, has anyone done a Bell test using that source of randomness, that intrinsic, maybe undeniable source of randomness that is human free will? Has everyone used that to make the measurement choices in a Bell test? Not until now. And so that's how we get to the big Bell test. Okay? That's really what the Bell test is all right. It's putting the human free will into making those choices to see whether in principle that could make a difference in the outcomes and whether we could stymie maybe the illusion of these correlations is just because the random number generators we've been using have not really been random, but maybe humans can do something different. Okay, that's the idea. That's the website. So it's not too late to participate, and I think Geoff is going to tell you more about how that works, and I'll pass over to... Oh, I think that's right. Yeah, I forgot. That's right. So Rob is going to do an introduction to Geoff, but yeah, basically Geoff is going to tell you all about this and also the real technology that lies behind the big Bell test in his lab and in other places. Okay.
Thanks very much for that, Howard. So the format of this evening is that we'll ask for discussions just a little bit later after Geoff has done his presentation. Howard, again, a fantastic presentation. So I'll ask Professor Geoff Pryde to come up and to do his talk now. So Professor Geoff Pryde is an experimental quantum physicist who works with photons, and somebody said in single particles of light. He investigates the fundamentals of quantum physics and how quantum systems can be harnessed to develop new technologies such as ultra-fast computers, ultra-secure messaging and ultra-precise measurement tools, as Howard had discussed already tonight. He's fascinated by the weird quantum world, and weirdness is useful. Professor Pryde is a Research Program Manager in the Australian Research Council Centre of Excellence for Quantum Computation and Communication Technology. A major initiative that links the world-leading Australian groups with each other and international partners to perform cutting-edge quantum science and technology research. He enjoys training the next generation of research, science and technology leaders through research projects in the classroom. In 2014, Professor Pryde was awarded the Pawsey Medal from the Australian Academy of Sciences for outstanding research in physics. Geoff, I'd like you to come up and give your presentation. Please welcome Geoff.
Thank you very much, Robert. It's a real pleasure, everyone, to be here tonight and to talk to you about the Big Bell test at Griffith University and a little bit about some of the other quantum physics research that we do in the lab and in our theoretical research teams at the Centre for Quantum Dynamics at Griffith University. So we've seen this slide of the Big Bell test. This map and these dots on it show where the participating organisations are. Everywhere you see a red dot on this map is a lab in which someone is doing a quantum physics experiment to do a Bell test or something very similar right at the moment, today on the 30th of November. And you'll see that there are two dots in Australia. One of those is Griffith University, it's my lab at the Nathan campus, and the other dot is UQ, which seems to have been moved to Rockhampton. But anyway, let's not talk about that. In any one of these labs where the Big Bell test is being conducted, the experiment will look something like this. There'll be a source of quantum entanglement, a pair of particles that are connected together in a quantum way. And those two particles, as Howard told us, are going to go out to two different measurement apparatuses, one for Alice, one for Bob, as we call them. And at each of those locations, a different measurement will be made out of a set of possible measurements that we can use. So here they're represented by different colours. At this particular time, a green measurement on this side and a blue measurement on this side. Measurements of certain physical quantities. Which measurement is chosen at each particular run of the experiment is being determined in the Big Bell test by random numbers that come from you, the participants who put random numbers into the Big Bell test game online. So these random numbers come to the labs through online servers, and at my lab, for example, they're choosing one out of a set of 16 measurements at each step of the experiment to make on a pair of particles. Those particles are measured and we get a result, one of two possibilities for each measurement outcome. Maybe we'll say a blue measurement on one side and the yellow measurement on the other side. Okay, we repeat this experiment many, many times, over and over again, a fresh set of data, a fresh set of entangled particles, and we look to see for correlations. In fact, in my lab, we're looking for anti-correlations. We're looking for the case where you get blue on one side and yellow on the other, or yellow on this side and blue on the other. It's still a correlation, it's just the other way around. Okay, and we're comparing that to see whether that's what happens or not. That's the signature of the quantum correlations, the non-locality that Howard talked about. And all of the experiments have slight variations on this, but this is what they're doing. So what we need to do, the Big Bell test at Griffith University and beyond, is really this set of things. We need some quantum systems that we can measure. In my case, they're photons. Quantum bits, quantum systems that have two states, a 0 and a 1, but the possibility of those two states combined, as I'll explain in a minute. We call them quantum bits or qubits. We need some entanglement. We need the particles to be connected together in a quantum way. We need a measurement apparatus to measure them. We need the random bits from free will. We need some kind of test that we can perform. Do the numbers that we get from the experiment beat some bound or not? Have we demonstrated non-locality or not? So some sort of way of measuring that. We use a test called quantum steering, which I'll say a little more about later. And of course, we need a team of scientists in order to do these experiments. So let me say something about the team in my lab, first of all. It's coordinated, and a lot of the work has been done by Dr. Raj Patel. Done an amazing job in getting it all up and going. And PhD student Fazad Junagani has contributed a lot as well. And every single person in my group, shown here in the photo below, has also contributed as well. And I think I saw Nora here in the audience earlier on. So, hi Nora. Well done, and well done to all of these people for the amazing effort that they've put in. So what they're working with in my lab is photons, single particles of light. You've heard about the Heisenberg uncertainty principle. You can't know the position and the momentum of a particle like a photon at any time, but you've probably also heard of wave-particle duality. What is light? Is it a wave? Is it a particle? What's going on? Well, the answer is somehow it's both at the same time. Okay, and what that means in practice, if we skip past really deep discussions, is that we can describe a photon, a single particle of light, as a chunk of energy which basically lives in a wave of electromagnetic radiation. And what I want to talk about tonight is what we call polarisation. It's which way the electric field of that wave is oscillating. Is it oscillating up and down, in which case we call it vertically polarised, or is it oscillating side to side, in which case we call it horizontal polarisation. And so when I talk about photon polarisation states, this is one of the things that I'll be talking about. Okay, we're used to polarisation in everyday life, I guess in a non-quantum way, because many of us have got polarised sunglasses, for example. Here's a picture. A photographer has taken this photo in the side mirror of their car, and it's reflecting what they're seeing on the side window of the car, and you can see some lights coming from some trees and is being reflected into the side mirror and coming back to the camera. There's no polarizer here, no Polaroid sunglasses in front of the camera. Okay. It turns out that the light that's bouncing off this window from these trees is very polarised, and if the person using the camera had a filter or some Polaroid sunglasses, as they've applied in the top half of this photo, this light that's reflecting off the window would be blocked out and you wouldn't see it anymore. Instead, you could see through the window and see the photographer behind. It's the same way that with Polaroid sunglasses you can see, cancel out reflections off water. You can look at different parts of the sky and see it dark in some places and light in other places, even during daytime. These are everyday effects of polarised light. In our lab, we look at polarised photons and use them to carry information and look at quantum physics tests. So why do we use photons? Well, as the fundamental science that Howard talked about, we're also interested in applications, secure communication, fast computing, precision measurements. And we've already known, even not in the quantum world, that light is a great way of carrying information. When you access data online that comes from a long way away, it comes in laser pulses that are carried through optical fibres, okay, carried by light. And it turns out that at the quantum level, light's also an excellent way of storing and processing information. I'll say a bit more about that later on. Let's come back to our polarisation qubits. They're two-state systems that, like Howard was talking about before. So I talked about horizontal and vertical, this orthogonal pair, this sort of opposite pair of states that we can distinguish perfectly from one another. If we've got a vertically polarised photon, we can put it into a measurement device and find out for sure that it's vertically polarised and not horizontal. Okay? But the funny thing is that photons can exist in a superposition or a combination of these two states at once. For example, if we have equal amounts of horizontal and vertical, we can make some diagonal polarisation, the light oscillating this way, or other diagonal, which we call anti-diagonal. Or in fact also circularly polarised light, where it spirals through space. Turns out that's a combination of these two. In fact, there's an infinite number of combinations of these two states, and that's a weird quantum thing. In some sense, it's like all of these states exist at once. So if we represented the polarisation state of light by a line that goes from the centre of a sphere out to the edge, then basically pointing any single direction on this sphere is a valid polarisation state of light. Okay, horizontal and vertical, diagonal and anti-diagonal. There are these pairs at opposite sides of the sphere that we can distinguish from one another, but there's all of these possibilities possible. That's very different from an ordinary classical bit, which only has two values, 0 and 1. Here, there's actually an infinite number of possibilities. Okay, that's weird by itself, but what we really need is entanglement. We need to take this a step further. And that's taking correlations that Howard talked about and this idea of multiple possibilities and smashing those two ideas together. We put those two ideas together and we come up with this weird quantum effect that Schrödinger described first as entanglement. This is what it looks like. Except that my pointer seems to be dead. Guess the batteries are flat. Okay, well, while I'm talking, I'll change the batteries. Yes, probably in here somewhere. Thanks. Okay, So here's our sphere, which represents the polarization state of light. And now we've got two photons. We need to have this entangled pair, and we've organized for them to be anti-correlated. So I'm imagining one photon we're going to label as green and the other one as yellow, even though we can't tell which one is which until we split them apart. If one of them is vertically polarized, the other one will be horizontally polarized. But we need to have a superposition of possibilities. So we don't know for sure. There's no pre-existing state, as Howard said. So we could, in fact, have the other way around. Maybe the horizontal one is, the green one is horizontal and the yellow one is vertically polarized. Okay, in fact, it's not only that, it's really that they could be pointing in this direction on the sphere, or in this direction on the sphere, or in this direction on the sphere, or in fact in any possible direction on the sphere. The green particle is in fact, its polarization state is in all possible directions, and the yellow one also in all possible directions. But here's the thing, whichever way the green one's found to be pointing, the yellow one will point in exactly the opposite direction. This is entanglement. And so if we make some measurement, we don't know if we'll find the green one pointing in this direction and the yellow one pointing in that direction, or vice versa. We can choose any polarization to measure, any different things, diagonal, vertical, anything. But whatever we find, when we find one in one direction, we'll find the other, if the particles are entangled. And this is what's different from Howard's dice example. In Howard's dice, you've really only got one case. The dice points, one dice gives you one value, the other one gives the other. You can't have all of these possibilities at once. Okay, so in the lab we need to actually make these entangled photons, photons that behave that way. How do we do it? We take a laser and we shine them on a certain kind of crystal called a nonlinear crystal, which sometimes produces pairs of photons. So the energy from the laser photon is consumed and it generates two photons of lower energy, conserving energy. And these things can be made to be polarization entangled in this state that we see here. Here's a picture of it in the lab. The green light is because we conduct our experiments in the semi-dark so that our detectors are not disturbed by background light, but we've got filters and can use particular colours of light to illuminate things. Here's the laser. The light comes around here, and right here's the nonlinear crystal. And pairs of photons come out, and one of them heads this way, one of them heads this way. They go into some optical fibres and are sent to other parts of the experiment. So we've got our entanglement. We can send them to different parts of the lab. We can do what we want with it now. So what are we doing in our experiment? We're doing this thing called quantum steering. And although steering is a concept that Howard himself recently formalised and gave us the mathematical details of, it really goes back to an idea of Schrodinger's, which we've already seen tonight. It's this idea that when one particle is measured out of an entangled pair, the result causes an instantaneous change in the other particle. When we measure in one direction, we know instantaneously that the particle on the other side will be measured in the other direction, no matter how distant. So that's what steering is. Of course, we could write it down mathematically, but I won't do that for you tonight. I'll just tell you that that's the effect that we're looking for in the lab, those kind of anti-correlations with these entangled photons. So we need to measure the photons in the lab, and we've got two copies of this particular apparatus. This is the measurement apparatus. A photon comes in this direction and travels through this set of optics here. And basically all this set of optics here is a very complicated polarizer, a very complicated pair of sunglasses where we can change which way the polarization axis is measured. Okay, and we can get two outcomes. Either the photon is polarized one way and comes here, or is polarized the other way and comes here, but we can just change whichever axis we want to measure. And what we do then is we pick some axis here, some polarization we want to measure, and the way that we pick that is using the random bits that you and people like you contribute through the Big Bell Test website. Okay, they come to the computers in our lab and then down to these devices here, which change the measurement direction, so we can choose all of the 16 different possibilities from 16 different equally spaced directions on this sphere. Okay, so what we're looking for is to see if one particle is measured in this direction, the other particle comes out the other port. Similarly, if the first one was polarized this way, the second one is like that, and then for every direction we choose on the sphere, according to our random numbers, we want to see the same thing. If instead we sometimes see, oh, they're both coming out in the same direction, sometimes different, sometimes the same, then there's no correlation. On average, that'll turn out to be nothing. and we'll find that this supposed non-locality, this supposed effect that we've just talked about tonight, isn't really real after all. Okay, so it's the 30th of November. These experiments are going on right now. The experiment's still running real time in my lab right now. And of course, Europe and North America and South America haven't come online yet. So if you're interested in contributing your random numbers, there's still time to do so. How do you do it? You just Google Big Bell Test and go to the website. When you get there, click on Contribute on the top of the page. And then there's a little game to play which allows you to type in zeros and ones and to see how random you can be in order to contribute your data. The game looks something like this. You dive into one of these levels and off you go. When you've finished one of the levels and you've contributed your random bits, you'll see a screen that looks like this. And it tells you, for example, that in CQC2T, the Centre of Excellence that Howard described, at Griffith Uni, 6 bits have moved the phase shifter. That's the polarisation measurement device that I talked about before. Okay, but when I ran this earlier, I also contributed in South America and in France and in Austria and China and Spain and so on. Okay, so all of these experiments are running, and my random data went there to do it. So you can try that later on. Please contribute if you're keen. We'd love to have your randomness play a part. Okay, so as I said, what we do is this quantum steering test. We take the inputs from human-generated randomness, we make the measurements, we take the outcomes, we combine them mathematically, and we look at how correlated they are, how often the answers came out opposite like we expect. And if they're bigger than some bound, some mathematical threshold, like the one that Bell derived, similar to that, then steering is real, this non-locality is real. If not, then maybe we've done something wrong in the experiment, or maybe the theory's wrong. Okay? And as Howard said, the particular take that we have is, does it work with human-generated randomness? Well, of course, our experiment's been running all day, so I can already give you an update on the preliminary data. Here's a screenshot that Raj sent me a little bit earlier on. This is what he looks at in the lab. Unfortunately, this isn't available online, but when he and the team run the experiment, they can see on any given trial that the string of 4 random bits that came in to 4 random bits is 16 different settings that came in here. They turn it to decimal. That means setting number 4. It's all automated, of course. They collect some data. They repeat this many times over, and they can get some answers. And here, this number here is basically the correlation function. If you multiply this by 100, it tells you what percentage of correlation you've got. So we're 97% correlated, and being good scientists, we also need to know how uncertain that measurement is, how confident we can be of it. And you can see we can be pretty confident. This is a small number. The bound that we need to beat to see non-locality is 0.51, and so we're more than 50 standard deviations above the bound. So it looks like, perhaps not surprisingly, from what we've seen previously, that non-locality, even with human-derived randomness, is a real thing. This is our preliminary data. We'll see more of it as when we analyse our data tomorrow and going forward from there. We're still collecting, so you're still able to jump in if you want to do that. Okay, so in the last few minutes, I would like to just say a little bit about what this is useful for. Howard's already given you a little bit of an overview of that, but from a more experimental point of view, I can say a little bit more. Okay, so the focus I'll have is at Griffith Centre for Quantum Dynamics, but of course there are labs around the world working on similar problems, including many in Australia and elsewhere that we collaborate with. So if you're interested in any of the things you see on the next few slides, which I'll have to go through quickly, please talk to us afterwards, or Google Quantum Dynamics Griffith, or look on your little handout to follow up with us later on. The motivation for this part of the talk is this idea that fundamental science, whether it's in quantum or any other thing, ultimately heads towards technologies. Okay, in the 1960s, the laser was invented. It was a fundamental science problem. No one really knew what to do with it. Today, we use it for medicine and industry and communications and laser pointers and whatever else. 1,001 applications. Okay, and we expect the same to be true. In fact, we already know some examples of how this will be true for quantum mechanics as well. In fact, we've already had the first quantum revolution. The basic ideas of quantum physics have been used for transistors, computers, for lasers, for atomic clocks, for GPS, things like that. Okay? But now these new ideas of superposition and entanglement that I've talked about tonight are leading to these new technologies like quantum computers, secure communication, precision measurement, the things that Howard introduced us to. And our job at Centre for Quantum Dynamics is to try and take a big step towards this quantum information technology by doing the science, the quantum information science that will make it possible, and starting to develop the technology as well. Howard mentioned that many of us, or several of us at CQC, Centre for Quantum Dynamics, are part of CQC2T, as we call it, this ARC Centre of Excellence. And in that, we do quantum communication and computation research with our partners here in these different Australian universities and something like 30 or 40 others around the world as well. Okay, a couple of little highlights from my lab. We do these steering experiments, but we're looking at how you can use them to make long-distance correlations for secure communications. And what we focus on in my lab is how you can overcome the effects of loss. Sometimes the photon gets absorbed in your optical fibre or something like that. That stuffs things up. What can you do about it? How can we make it a real thing by overcoming this loss problem? And we use quantum steering to do that. We've had a number of recent exciting results there. And in quantum computation side of things, we're looking for steps towards making this massive computational speed up. And one of the recent examples in my lab is doing simple quantum algorithms using a circuit of light, single photons, entangled photons, to make some sort of logic gate here that we can do simple stepping stone algorithms towards bigger and better things. One of our colleagues, Mirko Labino, is taking these optical circuits that we showed you before, those sort of, sets of optical elements that I showed you for the Big Bell test, and thinking about integrating them down onto small chips. In the same way you have electronic chips in your computer, these are optical chips that can carry single photons and other quantum states of light, can switch them into different paths, you can make complicated circuits, the next generation of devices for the manipulation of quantum light. So he's basically looking at the technology that can turn the basic science into something more practical, more realisable on an everyday scale. He and another colleague, Eric Streed, work with single atoms, single ions, single charged atoms trapped, which behave in a very quantum way because they're isolated from the rest of the world. You may have previously seen in Griffith publicity this shadow of a single atom. Shine light on a single atom and see the shadow that it casts, okay? That's this black dot here in the middle. That's from this lab here, and the idea to do this is to connect ions and photons to be able to have the quantum information that's on an ion transmitted to a photon and vice versa. So absorbing light by shining it on an atom and casting a shadow is one way of making a photon receiver. And then that light can be, in principle, re-emitted and put through Mirko's waveguides and then sent off to all sorts of other processing as well. On a completely different front, one of our theory researchers, Joan Vaccaro, is looking at converting heat into useful energy basically by thinking about entropy or randomness in a completely different way. By having a very low entropy reservoir, she can basically, is doing the theory of new kinds of heat engines, which will basically allow us to, in principle, grab useful energy as electricity from heat. One of the other things we're really interested in, and I've barely had time to talk about tonight, is quantum metrology. It's the idea that not only can we process information and transmit information securely, but we can use light and other systems to measure things very, very precisely, particularly when we use them at the quantum level. Okay? Well, why are precision measurements important? Well, precision measurement is at the heart of all quantitative science. If you want to put a number on something, you have to be able to measure well. Simple as that. And every time we've had advances in measurement precision, we've had new physics, we've had new technologies, we've had new developments as well. And one of the ways that this is happening in CQD is by our chair tonight, Professor Rob Sang, another colleague, Igor Litvinyuk, who basically used this device here, this beast of a laser, which takes up an entire sort of table, sort of from here to the wall and down there, out there. It's enormous, this beast of a laser, to basically be able to measure on time scales of 1/1000th of a second. Okay? These are almost the shortest pulses of light that can be made. Okay? And with these you can probe atoms, you can rip atoms apart, You can real-time make movies of physical processes in atoms and molecules, biological systems, whatever you're interested in, okay? You can measure quantum effects like quantum tunneling, find out, answer these fundamental questions, and then take the next step. How can we then apply these to new technologies? All right, I should stop and let you ask some questions. So in summary, quantum technologies promise advances in computation, communication, precision measurement, and more. These require fundamental quantum physics research, such as understanding what entanglement's really all about. That's what the Big Bell test is about. And the Big Bell test is one way that you can get directly involved in these efforts to study and control the quantum world. Okay, so contribute your random bits and keep an eye out for more exciting science and technology from CQD and Griffith University. Thanks for your attention.
Great, thanks very much for that, Geoff. Actually, Howard, would you be able to join us up here at the table, and we can have a little bit of a discussion. So, actually, it's an exciting time. Well, I guess it's probably always been an exciting time for science, but for me personally as a physicist, Geoff was actually showing some of the instrumentation that we have. I mean, Geoff has got these fantastic detectors that he's worked with colleagues in the US to detect single particles of light, or photons, and in fact the laser system that I have that looks at produces really short pulses of light. There's exquisite control of that light. And we also now have exquisite control over matter. We can actually use lasers to manipulate atoms and actually use those in experiments. So it's a really exciting time to test things that people really only dreamed of. For example, Richard Feynman, that Howard mentioned earlier tonight, back in the 60s, he basically said, imagine if we could ever move atoms singularly around atom by atom and build things. And in fact, Geoff showed a picture of, in fact, that type of technology, which has actually been available now for over 10 years. So it's an exciting time, and I'm sure Howard and Geoff are quite happy to take some questions from yourselves about tonight's presentation. Would anyone like to start? Yes, sir. Thank you.
Do we have
entanglement?
Yeah, I thought there was some spare mics for. There was some enormous number of mics, so.
See if we get this to work. Is that working?
Just a general question about entanglement. I suppose broadly how entangled is entangled. Like if you have two particles that have been entangled and you can only measure a subset of their properties. Could you use the entanglement to measure the other subset that you haven't measured on the other particle? Does that make sense? So if you were uncertain about, say, one of the complementary variables, could you measure that one that you're not measuring on the other particle if they're entangled?
Yeah, okay. Well, do you want to take it?
Go ahead.
You need to take it?
You have the first
so I think, yeah, maybe what you're getting at is, so Geoff talked about how when you have entangled particles in a particular state, that, yeah, if you measure them in the same direction, so to speak, with the same polarization, type of polarization on both of them, you always get perfectly anti-correlated results. And you're asking, well, maybe, at least I'm going to interpret your question as asking, what about if you measure in different directions? What does that tell you? So what you're talking about is exactly what you have to do for a Bell test. So in fact, for the full Bell test, which is testing for these non-local effects with the minimum assumptions, yeah, like on one particle you would randomly measuring in some direction, but the other particle would be some other direction, okay? And so it's not quite like the steering test which Geoff talked about. So it is precisely the fact that in Bell's original proof, he precisely used the fact that if you do measure in the same direction, you get perfect anticorrelations. But what happens if you measure the other one in a slightly different direction? And he used this sort of argument to actually, this is exactly how he managed to prove that there was no way to explain those correlations when you're not measuring in the same direction. So yeah, it is very closely related to the whole idea of the Bell test is very closely related to that idea. Yeah.
Okay, another question? Yes, sir.
How do you actually know that you've identified the particular atom that you're actually dealing with in your experiment?
Yeah, sure. So in my lab, we use photons, which are single particles of light. But in other experiments, they do use atoms, and the answer to your question is a little bit different. So I'll tell you both. In the atoms, one way of doing it is to trap a single atom basically in free space, in a vacuum, inside a vacuum chamber, and by shining light into that vacuum chamber and with appropriately chosen lenses, you can actually image a single atom, just like that shadow of a single atom thing that I showed you before. So because you know where the atom is, you can then use the same optics to shine light on it, which is how you make measurements on an atom. With the photons, the way we do it is that we know that they're born in pairs at the same time. There are ways that we can measure that, but we basically use the fact that they're born at the same time as a way of keeping track of where they're up to. They're born at the same time, we know how fast they travel, and so by timing our measurements really precisely, we can make sure that this one is connected to that one.
Another question? Yes. Oh, Cecilia, and then we've got one down the back. Don't.
This is a very curious question. You had a slide on time tunnel just now, mentioned. Are we close
tunneling,
to
was it?
time travel then? Is there a connection between the time tunnel that you had in your slide and time travel?
Tunnel time.
Oh, yeah. No, despite the very interesting sounding name, they're not the same thing. So tunneling is itself a really weird idea. Tunneling, if you took this idea of tunneling up to the classical scale, what it would be basically saying is, imagine I had a ball and I threw it at this wall. And I threw it just softly so that it would bounce off the wall, okay? We know that's what's going to happen. In quantum mechanics, it says that if we do that, sometimes the ball will actually sort of magically, it seems, go through the wall and come out the other side as if the wall wasn't even there. That's what quantum tunneling is. It's this strange effect that things that don't have enough energy to make it past some barrier can somehow appear on the other side of the barrier. And the question that Rob and Igor are answering is, how long does it take to go through there? Is it instantaneous when that happens? Does it just pop up instantly from one side of the barrier to the other? Or does it take some time to go through the barrier? It doesn't seem like the particle should be able to live inside the barrier, so that's the question. So it's not really related to time travel, but it's related to this weird quantum effect. How long does it take for a particle to do something that we don't think it should really even be allowed to do in the first place?
Anyway, there's some great controversy in the literature at the moment that actually shows that there's this actual time that really does take to go through there, and in fact the textbooks will actually tell you that it's actually essentially instantaneous, and so it's a pretty amazing time that we live in. We actually can conceive an experiment that can actually measure this and rewrite textbooks, which is a nice thing. So there's a question in there, sorry.
Talking about quantum and randomization, how does Bell test deals with superdeterminism?
Do you want me to do that? No. No, I'll do that.
Yeah.
Yeah. So superdeterminism is a term that I think Bell himself introduced, which is basically exactly what Gerhard Terft believes. This theory that everything was determined. So determinism in a normal sense is that there's the idea that physical systems, the way they behave is just to follow regular laws with no randomness, and a lot of things seem to behave that way. Superdeterminism says that all that is true and our free will is part of that as well. So that our free will is just an illusion. We can't actually make it a decision which is uncorrelated with other things, like it's whatever it was going to be, that's what it's going to be, and if that's correlated with the state of some particle in a lab somewhere else, then that's just the way the world is. So yeah, there aren't very many physicists who take that seriously, but there certainly are, and there are some very clever ones. Like I think I forgot to mention that Gerhard Terft is not a crackpot by any means. He's another Nobel Prize winner. So there are some very smart people who take this idea seriously.
This one here. This Jen hasn't asked you, just here. Thanks, Tom.
You mentioned that the photons are born at the same time and that you're keeping track of where they are by timing, but they're actually travelling at the speed of light or whatever, so what are we using to keep track of time?
Yeah, so the speed of light is very fast, but we can measure on incredibly short time scales. Okay, it's not too hard to measure on billionths or even trillionths of a second. So light travelling through air travels about 30 centimetres in a billionth of a second. Okay, so the scale of these experiments is usually on the metres or tens of metres or sometimes even up to kilometres, and so we can actually keep track of time, you know, tens, hundreds, maybe thousands of times, shorter times than that. So yeah, it takes some high technology, but not outrageously difficult. Yeah.
Okay, we've got a question, I think, from a Twitter feed. Is that
it's from YouTube this time.
YouTube, okay.
I'll try. So, are non-local phenomena limited to the entanglement revealed in the violations of the Bell inequities, or can local information and conserved quantities also move in a non-local way? That's all I've got.
I'm not sure that I completely understand the question, but I'll have a go at it. A physicist by the name of Kevin Resch and some of his colleagues, he was a postdoc at UQ for a while, he's now a scientist in Canada. He worked with the team in Vienna that Howard mentioned as part of things as well. He and his colleagues did an experiment where they showed that not only can particles be entangled, but in some sense entanglement itself can be entangled. So I can take a pair of entangled particles and the actual entanglement itself can be a physical property that I can entangle with something else. So the quantum world is even weirder than we've described it tonight. So yeah, all sorts of things can show this non-locality, not just individual particles. There was maybe a hint of that in the question, but I'm not sure if I quite got what was being asked.
That might come back.
We had another question over here. Oh, Damon's already gone that way.
Hi, I have a question for Howard. And you mentioned that the entanglement speeds should be slower than light speed. But based on the Bell's theory, it seems that the communication speed between the entangled particles can be faster than light speed. Why?
Why? Oh, well, so yeah, when I said I said there was an assumption that, which I called Einstein locality, which was that something which Alice does in her lab can't affect things that happen in Bob's lab faster than light, so faster than the time it would take light to travel there. That's an assumption that if you have to throw away if you accept the other assumptions in Bell's theorem. So that was the point of those assumptions, is that at least one of these has to be wrong. And so if you accept the other ones like micro-reality, macro-reality, and free will, then you have to say that the other one, the Einstein locality, must be wrong, and that yes, it's something going faster than light. And so they said yes, there are some physicists who think that is the best answer to the conundrum of Bell non-locality. Yep.
Thanks. I think we've got time. Yep.
If we took the idea of superdeterminism as something that's driving this, at what scale do you think the real effect either emerges or devolves within that discussion?
Scale in what?
How does it manifest? Can it manifest as an emerging property, or does it manifest only at the,
Yeah, okay, I think that's, it's a good question of how well, I'll try to interpret that it would be very strange that superdeterminism is something where our free will was constrained only when we were coming to do Bell experiments. Like, what's so special about doing Bell experiments? So if you believe that the reason Bell experiments come out the way they are, as the results from Geoff's lab that we've seen so far seem to be saying, then and then if you believe in superdeterminism, you'd have to believe it applies to humans as well. That really raises the questions about, well, what about all the other decisions which we're making in our life? Like, why? Yeah, it seems like everything we're doing would be super determined by, something that happened in the Big Bang. And is there, if that's the case, then you'd think that all sorts of weird things would be happening in the world, which don't seem to be happening. That's why personally I don't like the idea. But I'm not sure whether that's getting anywhere towards answering your question.
But a line in the sand hasn't started to emerge in terms of how these processes happen. It could be a location issue that emerges as some sort of...
Oh, right, in the sense that, yeah, there are many different things you could test in terms of... I mean, I think I said that the definitive Bell test had been done in 2015. But then nobody had done it with human randomness. But then there also will be the question of, can we combine the human randomness with the other aspects of those 2015 experiments which made them really definitive, which I didn't actually talk about. And that's even more of a challenge. So I think there's still a future for putting more and more of these constraints really on the theory by doing the experiments in better and better ways. That are going to rule out more and more possibilities. Yeah, so I think there's still a future for this.
Great, thanks. We're getting close to time. I've got one question, Howard. I mean, I do like the application sides of this research, and I noticed you talked about transporters and being teleporters, and being a fan of Star Trek. I'm just wondering, when are we going to be able to teleport between our campuses at Griffith?
Yes, that would be very convenient. Yes, yeah. But I wouldn't hold your breath. Yeah. Well, we might actually be able to do a teleportation experiment between the two campuses, and Geoff could probably say something about when that might happen.
Yeah. So. Well, indeed, this is exactly the kind of issue that we're addressing in our lab. One of the issues to doing these experiments over long distances with light is that when you send light through an optical fibre, it gets lost some of the time. And the further you send it, the more of it gets lost, and so the lower the data rates are when you try and send it over long distances. And when you send it over a really long distance through an optical fibre, eventually so much light gets lost that other noise gets in the way and it's impractical to do an experiment. And so what we do in our lab is try to come up with ways, and we've got several different ways of attacking the problem, of overcoming this loss, of trying to share entanglement between two really remote parties that are 100 or hundreds or perhaps thousands of kilometres apart. So the first step in the process is working out what the physics behind this is. The next step in the process is showing it over longer and longer distances, and then the final step of the process is using it for a real protocol, teleportation as part of quantum computation or secure communication or something like that. The first part, understanding how we can do the process, is something that we expect that we probably should have a good handle on within a few years' time. Rolling that out as a technology, maybe another couple of years past that, and then, really long-scale things as a mature technology, 10, 20 years, that sort of time scale. These are random numbers. They're a bit rubbery. We don't know what we're going to find in the experiments. Not literally random, but they're a little bit rubbery. But this is what we have aimed. This is what we have planned. This is the research that we've received funding to do. And people like Raj and Nora and the rest of the team that I showed you, that's what they do on a daily basis. We have fun with the big Bell test. We get people involved. It's real science. But most days we're working on these kinds of problems to try and take steps towards future quantum technologies.
Thanks very much for that, Geoff. Just out of the matter of curiosity, how many people in here have actually gone online and played the computer game? Yeah, a few? Oh, fantastic. Oh, that's good. I've done it as well. Yep. I'll tell you an interesting, funny story. This afternoon I asked my PA to get online and have a go at it. And she got on there and got on the 10, and she just went 10, 10, 10, 10. Her randomness was 0. And I said to her, that's not very random. She goes, but I'm really predictable. So in the end I said, well, come on, show me something random. And in fact, if you see there's actually a numerical score beside it, she actually got up to 40, which was, I think, pretty random. And so it was pretty remarkable to see that. Look, I hope everybody's enjoyed this evening as much as I have. There is some feedback form, so really, if you had the time, really appreciate if you could fill out the feedback form and let us know what you thought about tonight's event. I want to thank our speakers tonight, Geoff and Howard. It's been an entertaining night. I think many of you would have learnt some things, something about the weirdness of quantum physics that we live in every day. So please join me in thanking Howard and Geoff. I'd also like to thank Damien and Rima tonight as well. There's a lot of work in fact putting these together and ensuring people come, and particularly when you see a major thunderstorm coming this way, you always wonder how many people are actually going to turn up. So I thank you all for coming along tonight, and I hope that you'll spend some time out here on the deck. It's lovely out here. There'll be some nice drinks and some canapes, and of course you can interact with some of our speakers tonight and ask them some questions. So thanks very much. Good evening.